So in the previous lecture, we saw one natural strategy for sorting which you would apply when we do something by hand, namely selection sort. So now let's look at another natural strategy which all of us use at some point. So the second strategy is as follows. We have now a stack of papers, remember, with marks on them, and we have to compute a new stack which has the marks arranged in descending order from top to bottom. So we'll take the first paper of the stack we have and create a new stack. By definition, this new stack is now sorted because it has only one paper. Now we pick the second paper from the old stack and we look at its marks as compared to the first paper that we pulled out. If it is smaller, we put it below. If it is higher, we put it above. So in this process, we now have the new stack of two papers arranged in descending order. What do we do with the third paper? Well, the third paper can be in one of three positions. It can either be bigger than the two we saw before, so it can go on top, or it could be in between the two, or it could go below. So what we do is we scan from top to bottom, and so long as it's smaller than the paper we have seen, we push it down until we find a place where it fits. Okay? So we insert the paper that we pick up next into the correct position into the already sorted stack we are building. So we keep doing this for each subsequent paper. We'll take the fourth paper and insert it into a correct position among the remaining three, and so on. So this is obviously called insertion sort. So let's see how it would work. So what we do with this same list that we had for selection sort is, we will pick up the first value and move it to the new stack, saying now I have a new stack which has exactly one value, namely 74. Then when I pick up 32, since 32 is smaller than 74, I push it to the left of 74. Now 89 is bigger than both, so I keep it on top of the stack at the right end. 55 I have to now look with respect to 89 and 74. So it is smaller than 89, so it goes to the left of 89. Then I look at 74, it's smaller than 74, it goes to the left of that. So eventually it settles down as 32, 55, 74, 89. 21 similarly, I have to start from the top and say smaller than 89, smaller than 74, smaller than 55, smaller than 32. So it goes all the way to the left. And finally 64 will move down two positions past 84 and 89 and 74, but it will stop above 55. Right? So this is how insertion sort would build up a new list. You keep picking up the next value and inserting it into the already sorted list that you had before. So we start building a sorted sequence with one element, pick up the next unsorted element and insert it into the correct place into the already sorted sequence. So we can do this as we did with insertion sort without building a new sequence. And here is a function insertion sort defined in Python which does this. So what we will assume is that at any given point, we have our sequence from 0 to n minus 1. And there is some positions so that up to this point, everything is sorted. And now what I will do is I will pick up the next element here and I will move it left until I find the correct place to put it, so that now the sorted thing extends to this level. Right? So we take a sorted sequence of length I and we extend it to a sorted sequence like I plus 1 by inserting the I plus 1 in the current place. Right? So we are going to take this position, the slice end. Right? The slice end is going to be the last position that we have sorted already. So this is supposed to be slice end. So we say slice end starts from the value 0 and goes up to the n minus 1th position. Right? And at each time, we look at the value so actually the slice is up to slice n minus 1, sorry. So slice end is the number of elements that we have sorted. So we look at the value immediately after that, which will be the position called slice end. And so long as this position is bigger than 0, and if the value at that position is strictly smaller than the value at the previous position, we exchange these two. Right? So what we are doing is that we are saying, to draw it again, so we have an already sorted slice from 0 to slice n minus 1, and we have this position slice n. So we then assume that this is sorted, so we compare with this value, and if this is smaller, then we exchange it. Now if we have exchanged it, that means that this value has now gone here. So now we again compare it to the previous value, and if it is smaller, we exchange it. So again, this means that it goes one more position. So we just keep going until we find that at this position, the value to the left of it is equal to or bigger than this, sorry, equal to or smaller than this. So we should not swap it, and we have it in the correct position, right? So that's what this is doing. So long as you have not reached the left-hand end, you compare the value you're looking at now to the value to its left. If the value to its left is strictly bigger, this one must exchange with that. And then you decrement the position. So let's run this the way we have written it on this particular sequence. So what we do is we initially assume that this thing is unsorted. So our first thing is here, okay? And so when we sort it, we just get a sorted list of length 1, which is 74. Then we look at this and we must insert it into this list 74. So since this is smaller than 74, it gets exchanged, and we get now a new sorted list 3274. And now we must insert 89 into this list, right? And now we see 89 is bigger than 74, so nothing happens. So this list now is sorted from 32 to 89. Now we try to insert 55 in this. So we will first compare it with this, and this will say that 55 is smaller than the value to its left, so we must exchange. Now we will compare 55 again to the value to its left, again we will exchange. Now we will compare 55 to the value to its left, and there is no change. So now we have a sorted list of length 4. Similarly, we will take 21, right? And we'll compare it to 89. Since 21 is smaller than 89, it will swap. Since 21 is smaller than 74, it will again swap. Since 21 is smaller than 55, it will swap. Since 21 is smaller than 32, it will swap. But now the position, will swap. And now the position is 0. So we stop not because we have found something to the left, which is bigger, but because we have nothing to the left. So we have two conditions, if you remember that algorithm. It said that either pos should be positive, the position should be greater than 0, or we should compare it to the value on its left. Right? So in this case, we have no value to its left, so we stop. So how do we analyze this? Well, at each round, what are we doing? We are inserting a new value into a sorted segment of length k. Right? So we start with the length 0 segment. We insert one value to it, we get a sorted length of sequence of length 1. We insert a value into that, we get a sorted sequence of length 2, and so on. But in the worst case, when we are inserting, we have to take the value all the way to the beginning of the segment. So sorting a segment of length k in the worst case takes k steps. So again, we have the same recurrence, not expression that we had for selection sort. It says that t of n is 1 plus 2 plus 3 up to n minus 1, which is n into n minus 1 by 2, which is order n squared. Okay? So again, remember that this is n squared by 2 minus n by 2. And so this is the biggest term, and that's what we get here. So once again, let us see how insertion sort actually works in the Python interpreter, and we will see something slightly different from selection sort when we run it. So first, let's look at the code. So this is the code that we saw in the slide. Okay, so it just keeps scanning segments, keeps taking a value at a position and inserting it into the already sorted sequence up to that position. So if we start the Python interpreter and say import this function, and then as before, if we, for example, take a long list, and sort it, okay, then L becomes sorted, right? So before L was in descending order, now we sort it, and now L is in ascending order. Now as before, what we said is that if we try to do this for a length of around 5000, then it will be much smaller, much slower, right? So you can see it takes a long time. Right? And that's because insertion sort is again order n squared sort. So though it does it eventually, it takes a long time. But there's a small difference here. So suppose we do it the other way. Suppose we take a list which is already sorted, and now we ask it to sort. Then it comes back instantly. Why should this be the case? Well, think about what's happening. Now, the list is already in sorted order. So when we try to take a value at any position and move it to the left, it immediately finds that the value to its left is smaller than it, so no swapping occurs. So each insert step takes only one iteration. It doesn't have to go through anything beyond the first element in order to stop the insert step. So actually, if we take even a large value like 10,000 or even 100,000, this should work. Right? So insertion sort, when you already have a sorted list, will be quite fast because the insert step is instantaneous. Whereas this doesn't happen with selection sort, because in selection sort, in each iteration we have to find the minimum value in a sequence, and with no prior knowledge about what the sequence looks like, it will always scan the sequence from beginning to end. So the worst case for selection sort will happen regardless of whether the input is already sorted or not. Whereas insertion sort, if the list is sorted, the insert step will be very fast, and so you can effectively sort larger things. So in that sense, insertion sort can behave much better than selection sort, even though both of them technically in the worst case are order n squared sorts.